What you're about to watch is the continuation of the multi-threading chapter. In this chapter, we're going to talk about thread pool, callable interface, semaphores, blocking queues, live lock and starvation, immutability, etc. Keep watching. In this video, we're going to talk about something called a thread pool. For this purpose, I want you to open this file, thread pool example, under the project Multithreading Extended. In here, I'm creating a thread and then I'm starting it. We can certainly make use of a lambda expression in here. Let's do that. It's going to be as simple as that. There we have the lambda expression and everything works well. And since we're calling this method start only once, we can do it in line right here. Now we can get rid of this as well as this. Let's save the file and run the program. Works perfect. Now this statement in here is actually a combination of two sections. Number one is creation of thread and starting it, and number two is the task that this thread is performing. In this case, it's just a sysout statement with some text which will be displayed on the console, but you could have a very big task performing very complex computations. For the sake of this example, I'm just going to use a sysout statement. Let me separate this section out. That looks more meaningful. Now this lambda expression would be of type runnable interface. I'm going to call it a task equals the lambda expression. And I want this thread to execute this task. The program will work just as before. Pretty well and good. Now what I wanted to do is I wanted to create 10 different tasks and execute them simultaneously. And for this purpose, I'm going to create a list that constitutes list of elements of type runnable interface. I already have the code ready with me. I'm just going to copy it and paste it over here just to save your time. So I have a list in here. Let's do Ctrl+Shift+O to import required classes or interfaces. I'm calling it tasks because it's going to constitute list of tasks, and each task is a lambda expression of type runnable interface, of course. And using add method, I'm adding all these tasks just as you see it here. Now the next thing that I want to do is to execute them simultaneously. I'm going to make use of the for each method in Java. So for each task of type runnable, from the task I'm going to perform this. Let's run the program and it works perfectly well. We can certainly make use of a stream instead of using our traditional for each loop. Let's do so. Let's comment this out. All I'm going to do is say task.stream.forEach, and for each and every task I want it to perform exactly same thing. Let's paste it over here and we're done. The program runs just as before. Although this program looks okay, we have a very serious problem in here. The problem in here is for each and every task, we're creating a thread, maintaining the state of the thread, and destroying the thread once the task is finished. We're doing it for each and every task in here. We already know that creating and maintaining a thread is an expensive process. It will cost us processor utilization and memory. And say if you have 1000 tasks to be performed, and if you create thread for each and every task like this, you will soon run out of memory and your application would crash. Even if your application wouldn't crash, at least it will affect you in terms of your application performance. So to address this problem, we have a thread pool. The concept of thread pool goes like this. We create a fixed number of threads regardless of number of tasks in hand to be performed, and all the tasks will be performed by those fixed number of threads. The best way to understand is to take a look at one such example. So the first thing that we need to do is create the thread pool. For that purpose, I'm going to use execute a service. I'm going to call it thread pool, as it would constitute a pool of threads. And in here, I'm going to say executors dot new fixed thread pool. And in here, we're going to give some number. I want this to be 5. Let's import the class. Now, what we have achieved with this instruction is that we have initiated the executor service, and then it's going to take care of creating a pool of threads. In this case, it's going to be 5 threads. Until this point, those threads are not going to perform anything because we didn't ask the executor service to perform all these tasks. You can think of executor service as a company or a service provider who is going to take in the tasks given by the customers, and the service or the company will then assign each one of the tasks to the workers in the company. The workers in here are nothing but the threads which it has created. So let's see how we can assign the tasks to the executor service. Again, we can certainly make use of the streams. I'm actually going to make changes to this instruction to feed the tasks to this executor service or the thread pool, whatever you call it. In here, I'm going to say thread pool dot, we have a method called execute. We're asking the executor service to execute a certain task. In this case, we're assigning all our tasks using the for each method. Now, as a programmer, we're not really taking care of managing these threads. It all be taken care by the executor service. For instance, we didn't create the thread explicitly on our own using new thread, and we didn't tell which thread to execute which task. Those are all be handled by the executor service. So as you keep adding the task to the executor service is going to ask each one of these threads to execute the task. So now the executor service is not going to perform all these tasks simultaneously. It will take 5 tasks at a time, as there are 5 threads in the thread pool. The rest of the task will be waiting in the queue until one of the threads finishes executing its respective task in hand, and so ultimately all these tasks will be performed by these 5 threads. So no matter how many tasks you have, be it 10, 100, 1000 or 10,000, all those tasks will be performed only by these 5 threads. The best way to understand what this method does, the new fixed thread, is to read its description. Creates a thread pool that reuses a fixed number of threads, and at any point, at most n threads, in this case it's 5 threads, will be active processing the task. And that's very obvious. It's going to perform at most of 5 tasks simultaneously, and if additional tasks are submitted when the threads are active, they will wait in the queue until a thread is available. And that's what I said. Let's try to run the program and see what happens. All the threads are executed simultaneously, and at max only 5 threads can be executed simultaneously. But note that the program is never going to end. We need to shut down the executor service. For that, we're going to call the method threadpool.shutdown. And what this method does, let's go through the description. Initiates an orderly shutdown in which previously submitted tasks or executed, but no new task will be accepted. So let's run the program now, and program gets terminated. And if you try to assign a task to the executor service after you shut down, we're going to get an exception. Let's try doing so. I'm going to say task 11 executed. Let's end with a semicolon and run the program. You got an exception saying rejected execution exception. That makes complete sense. And finally, just as we have a fixed thread pool, we also got many such mechanisms provided by the executor service, and you can explore them in here. We got new cached thread pool. So it's going to create a thread pool that creates new threads as needed, but will reuse previously constructed threads when they are available. We can make use of this in this context. Let's run the program, and pretty well and good. Essentially, the executor service will actually decide how many threads to create based on the task available, etc. You don't have to make a wild guess on number of threads to be created on your own. But let's undo. We also got many such methods. For example, new single thread executor. It's going to create an executor that uses a single worker thread operating off an unbounded queue. So basically, this is not going to create multiple threads. It's just going to be only one single thread that will perform all the tasks sequentially. You'll see the usefulness of this when we talk about callable interface, which will be in the coming videos. So likewise, we got many such methods. I would really encourage you to go to these descriptions and explore and experiment. And I believe that by now you're capable of exploring Java concepts on your own. That's the primary intent of this course. The intent of this course is not to explain each and every method that Java offers. The intent of this course is to make you stand on your own legs. So go and explore all these methods. They're pretty self-explanatory if you read the description. See you in my next video. In this video, we're going to talk about callable interface. Take a look at this example. I'm creating a runnable task, and I'm running it by creating a new thread, just like so. One of the issues with the runnable task is that it cannot return a result. For example, I can't say return x plus y. This is going to give me a compile time error. And that's very obvious because if you take a look at the interface, the method run is not going to return anything. It is returning void, which means nothing. So same goes in here as well. So what can we do? We can make use of the callable interface, which is going to return a generic parameter. Now this could be integer, this could be double, this could be your own object, whatever it is. You can certainly make use of callable interface. Let's import that. Now we don't have any compile time errors in the task, which is a callable task. In here we certainly will have an error because unfortunately the thread constructor will not accept a callable task. What we need to make use of is the executor service. I'm going to say executor service, let's give it some name, equals executors dot new single thread executor. Control Shift O. Now this instruction is going to create an executor service with just one single thread. This is where this method will come in handy. Since you can't make use of the thread constructor to deal with callable task, you can use the executor service just like so. And you will use this object and call the method submit. The execute method is going to accept runnable interface as an argument. So we need to use the method submit, which will accept a callable task. And we're going to submit this task. And after you do so, just as in our previous example, you're going to call the shutdown method. Executor service dot shutdown. Now we don't have a compile time error. But how are we going to get the value being returned from this task? The submit method is going to return an object called future. The future object is going to hold the returned result. Let's see how we can make use of it. I'm going to say future. The future is going to accept one generic parameter. In this case, we want it to be integer because that's what the result type is going to be. By the way, let's make this as integer just to avoid the confusion. Integer, and even this is going to be integer. Let's call this future. Let's do Ctrl+Shift+O. Now if you take a note, the callable interface is accepting one generic parameter, and that is the return type of this method call. In this case, it's integer because compiler can figure that out by looking at this code inside the lambda expression. So this will work. Coming back on the future object, you're going to make use of a method called get, future.get. Now the call future.get is going to keep the calling thread, in this case it's the main thread, in waiting state until some result will get returned from the callable task. In this case it's going to be pretty quick. So let's put another instruction in here, say thread.sleep, say 10 seconds. Now you might be wondering why the compiler is not complaining about the checked exceptions that the sleep method can potentially throw. Is because the call method in here is also going to throw the exception object. We'll talk about it in a minute. Let's continue with our example. But at least we should be seeing a compile time error in here. The reason we don't is because we're already dealing with those exceptions using the throws keyword. So now we should get a compile time error. Let's handle the exception with the try catch block. Let's get rid of some of these comments in here. That looks a lot cleaner. Now what we want to do is we want to use the sysout statement just to be able to print the result that this task is returning. So that's it. Let's run the program, and after 10 seconds you should see the result 30. There you have it. Sometimes you may not want to wait for the task to get finished. You want to wait for a certain period of time, after which you want to stop the operation. For that, you can make use of some of the methods available in the future object. For instance, let's say we wanted to wait for 5 seconds in the main thread. Thread.sleep, say 5 seconds. Again, this is going to throw the exceptions. Sorry about all the mess in here. Let's bear it for some time. I'm going to say future. I'm going to put it in an if clause. So it's going to be future.isDone. This method is going to return a Boolean value. If it returns true, that means the task is done, and if it is false, it's the other way. So if the task is not done, what we want to do is we want to say future.cancel the operation. This cancel method is going to take in one Boolean parameter. In this case we want it to be true. Why it has to be true? Go ahead and read the description. It says true if the thread executing this task should be interrupted. Yes, we want the thread executing this task to be interrupted. Otherwise, in-progress tasks are allowed to complete. So we'll keep it as true. Now, the program or the main thread is going to wait for 5 seconds, after which it's going to cancel this task. And we already know this is taking 10 seconds, so this should come first. Let's run the program. You see cancellation exception. The exception is thrown by this method get because we cancel the operation before the result is already present. Now if you observe, the program didn't stop. Let's run it again. Because we got an exception in the main thread, let's stop the program explicitly and let's deal with that exception. I'm going to use another catch block for the get method. This time it's going to be exception. Now let's run the program. We should see a proper result. Program got terminated. Pretty well and good. Likewise, there are a couple of other exceptions that this get method throws. You can see them in here with the description. Anyway, let me just undo all those changes. I just wanted to explain you that you can interrupt the task if you wanted to. So one another thing about the callable interface is that the call method is going to throw an exception as well, unlike the runnable interface whose method run is not going to throw the exception. And in fact, we have already looked at an example, the sleep method. Whatever the exception that the sleep method can potentially throw needs to be handled in the calling thread, and that's why we have to put the try catch block in here and deal with such exceptions. So that's it on the callable interface. By the way, you can also make use of a fixed thread pool for callable tasks as well. Let's take a look at an example of it. To save your time, let me just write the program and then I'll get back to you. So in here, I've created an executor service with a fixed thread pool of size 5, and I'm using the for loop to submit the same task 10 times to the executor service, and all these 5 threads will be activated with the task being submitted. At the same time, the future object that each one of these submit method returns, I'm going to store it in the list. I'm looping through all the future objects and trying to get the result. It's as simple as that. Finally, I'm doing the shutdown. Let's run the program and we should see the results of all these 10 tasks, which is going to be 30. There it is. It's as simple as that. See you in my next video. In this video, we're going to talk about semaphores. We know what a synchronized section is. The synchronized mechanism will give mutual exclusive access to only one thread at a time. If you run this program, since all these threads are trying to access the same section of code, the synchronized section, you would see these threads being executed one by one with a timing interval of 5 seconds. I'm not going to run this program to save your time. If you're interested, you can run it. But at times, you might want to give access to this section of code to not just one thread, but a limited set of threads. For example, you wanted to let 2 threads at a time to enter inside this section of code. Then the answer is semaphore. That's when you're going to use semaphore. The first thing that you need to do is to create the semaphore using the class semaphore. I'm going to say static semaphore. I call it semaphore, all lowercase, new semaphore. This is going to create an object of semaphore. Now the reason why we have an error here is the constructor of semaphore is going to accept an argument. and that makes sense. This argument is nothing but a numerical or the limit of this semaphore. If you say 2, that means the semaphore would constitute 2 locks that 2 threads can acquire and release. Let's take a look at the example and then you'll understand. So instead of saying synchronized, I'm going to say semaphore dot acquire. The first thread that's going to enter inside this section is going to acquire one of these 2 locks, and I'm going to say semaphore dot release. It's going to release the lock. While the first thread is still executing this section of code, the second thread that enters inside this section is going to acquire the second lock, which is available. Once the second thread acquires the lock, there are no locks to be acquired, which means the rest of the threads will have to wait until one of the locks gets released. So if you run the program, you would see 2 threads executing at a time. Let's run the program. T1, T2, and then they both will wait for 5 seconds, like you can see it in here, and then T3 and T4 entered, T5 and T6. Great. In this video, we're going to talk about inter-thread communication using a blocking queue. In other words, we will understand how 2 or more threads are going to communicate each other using a blocking queue. Consider the following scenario. Let's say we got a couple of threads, T1 and T2. We want these 2 threads to communicate each other. And the way it works is, thread T1 is going to generate a list of objects, and we want thread T2 to consume all those objects. The way it's going to work is by using a queue. We know what a queue is. The queue is going to have a certain size. Thread T1 is going to keep inserting elements into the queue, and simultaneously thread T2 is going to take those elements one by one. Let's call thread T1 a producer, as it is producing a list of elements, and T2 a consumer, as obviously it's going to consume those elements being produced by T1. Now the problem with this approach is thread T1 can try to insert an element even though the queue is full. Similarly, thread T2 can try to read an element when there are no elements left in the queue. In both these cases, an exception can occur. In programming world, this is called a producer-consumer problem. The solution to this problem is, instead of using a queue, use a blocking queue, and that will solve the problem. The way the blocking queue mechanism works is, thread T1 is going to keep on inserting the elements in the queue until the queue is full. And once the queue is full, the blocking queue mechanism is going to block the thread T1 to stop inserting the elements in the queue. Meanwhile, thread T2 keeps on consuming those elements. And at any given point of time, if there are no elements left in the queue to be read, then the blocking queue would block thread T2. So doing so, we got rid of the producer-consumer problem. Let's take a look at this example programmatically. In order to save your time, I've already written the code for you. Let me walk you through this code. The first thing that we need to do is to create those 2 threads, one being the producer, the other being the consumer. Here we have the code for producing the element. But before that, I've also created a blocking queue like so. Now this instruction in here is going to create a blocking queue of size 1. Let's make it 3. That makes more sense. So the producer is going to keep inserting elements. By the way, this method is called as part of this thread, and in another thread we're consuming those objects. So the way we are inserting in the queue is by using the method put. We're just using a for loop to insert the ith element, and we're going to loop through about 10 times. So we're going to be inserting 10 elements into this queue. Every time we put an element, I'm also printing, just for us to be able to see what's happening. Similarly, we got another thread which is going to consume those objects, and in here I'm trying to get the element by using the method take of the blocking queue, and this instruction is going to take the element using the FIFO approach and is going to return an integer, because that's what the type of elements that we're inserting. And every time I take the element, I'm also waiting for a second, and I'm printing what that item is. Let's run the program and see what happens. If I run this program, you would immediately see 3 elements being put, because that's what the size is in here. After inserting 3 elements, this thread in here is going to be blocked right here, because we cannot insert any more elements. So the producer will be blocked by the blocking queue mechanism. On the other hand, the consumer will keep consuming those elements every 1 second, and as soon as there is one space available in the queue after consuming, the blocking queue mechanism is going to resume the producer thread, and it will keep inserting. And again it will get blocked once the queue is full. Similarly, once we insert all the elements, and once all the elements are consumed, the blocking queue mechanism is going to block the consumer thread right here in this instruction, because there won't be any elements to be consumed. But in this case, we're exiting out of this loop once after we reach the item count, which means we're never going to see the consumer thread being blocked, but we will definitely see the producer thread being blocked. Let's run the program and see the output. Let it finish and then we'll go through it. We have the queue size of 3, and so 3 elements were inserted by the producer thread, after which the producer thread is blocked. And after the consumer thread reads one of the elements from the queue, the blocking queue mechanism again resumed the producer thread to put another element. In this case it's 3. Now you might be wondering why we have 4 elements shown up in here. That's because after the consumer takes the element and before we printed it on the screen, the producer thread was resumed and resulted in another element to be inserted into the queue. So don't get confused by looking at the output. So it has essentially blocked the producer thread after inserting the first 3 elements, and then the consumer consumed an element. Again, one element is put by the producer, and it kept on going and going until all the elements were put and all the elements were consumed. Finally, we got this program terminated. Now let's see what's going to happen if you try to consume more elements than what they are in the queue. Let's say 100. In this case, we would definitely reach to a point where the queue is empty, but still we're trying to consume elements. In this case, the blocking queue mechanism is going to block the consumer thread until some element gets inserted, which will never happen. So by running this program would result in running forever. Let's run the program. There it is. There it is. All the elements are consumed, but the consumer thread is not terminated. And that's why you need to handle it wisely, just like so. And by the way, the blocking queue is an interface, and one of the implementations of that interface is array blocking queue. In this case, internally the queue uses essentially an array. Likewise, we have got many such mechanisms. We got the delay queue, linked blocking queue, priority blocking queue, etc. The job of all these mechanisms is to provide the functionality of blocking queue, but they differ in terms of performance and the way they deal with thread communication. You can easily go through the documentation of this implementation, and I bet it's all self-explanatory. Alright, see you in my next video. In this video, we're going to talk about some of the problems existed in multithreading programming. We've already talked about what's a deadlock. In this video, we're going to talk about something called a live lock and a situation called starvation. In case of deadlock, two or more threads are going to wait for each other for the lock to be available. We've already talked about it. But in case of live lock, both the threads are going to be alive. Unlike the deadlock case where the both threads are blocked, they cannot progress with executing the task in hand. But in here, in case of live lock, both the tasks are going to execute forever. And for a reason. Take a look at this example. Assume that there are two friends. They are friends in their childhood, and they happen to meet each other, say in a shopping mall, after say 10 years. They both see each other, Krish and Jia. They both wanted to talk to each other, but then nobody wants to initiate first. Krish is going to wait for Jia to say hello, and vice versa. Jia is going to wait for Krish to say hello first. And that's exactly what we're doing here in this logic. The initial state of said hello is false because nobody said hello. And Krish is going to check to see if hello is being said by the other person. If not, he's going to wait for 5 seconds. And he keeps waiting forever until hello is said. On the other hand, Jia is doing exactly the same thing. She's expecting Krish to say hello. And both these parties are never going to set this flag to true. If I run this program, both these threads are going to wait for each other forever. Let's run the program. And you would see for every 5 seconds, you're going to see these messages getting repeated. And this happens forever. Let's stop the program. So the solution to this is pretty obvious. You should never write such kind of a logic where the execution will never end. Now let's talk about a situation called starvation. Thread starvation is a situation where threads will keep waiting forever or starve to death because another thread enters the synchronized section and it remains there for a very long period of time or forever. In this example, we have a synchronized method in which we're trying to deal with a file like so, and every thread wanted to create a file and write some content in it. In this case, the first thread that's going to enter inside the synchronized section will never finish the task because the code is having a bad logic, something like this. In here, we're looping through forever, and due to this, the lock will never get freed, and so other threads cannot enter the synchronized section and acquire a system resource or write content into some kind of a file. Let's run this program and see the output. So one of these threads has entered inside this and created this file in the location testdir. Let's go there. Here I am. So thread T1 entered first and it has created the file writing some content into it. But then it's stuck in this logic. No other thread can ever enter this section. The program goes forever. Let's stop this. So the solution is, again, you shouldn't have such bad logic. Let's get rid of this and then run the program, and all the threads are going to have opportunity to create the file and write some content in it. Let's go to that directory. Here we have them. And program finishes executing. Thread starvation can also happen when, say, you have 10 threads, out of which we gave a couple of threads the least priority. The threads with least priority may not get enough CPU cycles to get executed. So these two threads are again starving. That's it on this video. See you in my next video. In this video, we're going to talk about immutable objects and how it's going to add value to multi-threaded programming. We already know about string. A string is immutable, meaning once the string is created, nobody can ever change it, which makes it qualify for usage in multi-threaded programming. No matter how many threads are accessing a string variable, none of those threads can actually change the string. In other words, no thread can actually change the state of string object. So just like a string, we can actually create our own immutable objects. In this case, the person object in here is immutable, and for that, you need to follow certain guidelines while creating the person class. First of all, you need to make the class final, which will make this class non-extendable. That means you cannot create another class extending the person class and extend the behavior of it. You're going to get a compile time error. So we're preventing overriding. There's no overriding of behavior. Also, all the fields that you define in here, make sure they are final. By making so, you can only have a value assigned to this variable right when the time you create the object. And that's what we're doing in this constructor. We're assigning a value to it. And if you try to assign some kind of a value to this variable, again, it's going to throw a compile time error. So having a setter method for this variable doesn't make sense. Let me just uncomment this piece of code and you will see a compile time error saying the final field person.name cannot be assigned, and that's very obvious. So we can only have a getter which will get the name, and in here we have created an instance of that class which is an immutable object. You cannot change the some name to something else because there is no provision to do so. You cannot have something like object.set variable or whatsoever. We're not allowing it. In fact, compiler is complaining. Also, let's talk about string buffer and string builder classes. We know that string is immutable, but if you want a string that is mutable, then you can use string buffer, just like so. And you can use the methods inside it. In this case, I'm using the append method to append the string to the existing string. And this will actually modify the original string. This is mutable in this case. And if I do sysout, you're going to see the combination of these two strings. But that's not going to be the case with string. I've created a string object and I'm using the concat method of the string to concat this string. And when I do sysout str, this is only going to print this piece of string. That's because string is immutable. Let's run the program. There it is. Now you may ask me when to use string buffer over a string. Well, the string buffer is actually going to make use of buffering mechanism to perform all the string operations more efficiently. So string buffer will have some performance benefit compared to using a string. But I said string buffer is mutable. So should we use string buffer in multi-threaded programming? The answer is still yes. All the string buffer is mutable. All the methods inside the string buffer are synchronized. If you go deep into it, you can see the word synchronized in each and every method. So this is thread safe. But that being said, when you have all the methods as synchronized, that's going to cost us some performance, because at any given point of time, only one thread can enter inside the synchronized block. But based on your design, you need to make your choice. We also have something called string builder. Let's have it in here as well. It's going to work the same way that the string buffer works, but the methods inside the string builder are not synchronized, which means it's not thread safe. When you have only one single thread or a very limited set of threads, then you can use string builder over the string buffer. Let's run the program and you would pretty much see the same result. See you in my next video. Alright, we're not really going to talk about anything in specific in this video. I just want to point out that there are many different classes and interfaces present in the Java Util concurrent package. Please go ahead and explore them. You can just understand what each one of these classes does just by reading the description. If you go down a little bit, you can also find a bunch of collections. We've talked about hash map, for instance, in our collections chapter, but in here we got the concurrent hash map, which actually implements the map interface. And the purpose of this collection is to use hash map in the context of multi-threaded programming. Likewise, we got many such classes. So you don't want to use a hash map, a normal hash map, when you're dealing with multiple threads. That's going to cause a lot of issues. So just go ahead and explore all these classes and interfaces. And I bet you don't like me to go through each one of these classes and give an example about it. Because guess what? We just don't want to dedicate our life in just learning. We want to do something from what we have learned. And if I have to go through each and every thing that Java offers, it's going to take forever. I will keep teaching you and you will keep learning. And that's never going to end. But what I made sure is that I have introduced you all the key concepts present in Java. And you're now capable of exploring new concepts on your own. So with this video, I think we're done with this chapter of multithreading. See you in my next video.
I hope you enjoyed this tutorial. Please like and subscribe. The link to the next part of this course is in the description below. Also, if you want to learn Java with practice, with quizzes, assignments, coding puzzles, and interview questions, I cannot do that on YouTube. So you need to take this course on my own website. The link is in the description below. I'll see you in the next part of this course.